Hi everyone, my name's Dr Nathan Boase and I'm the 2021 RACI Queensland O'Donnell Schools Lecturer. It's a great pleasure to be joining you virtually today. The RACI, or the Royal Australian Chemical Institute, is the peak body for chemists of all of Australia. They represent us as a profession, but they also like to engage with the public to explain to the public about chemistry, chemical science, and chemistry as a career. My job is to visit schools this year, just like yours, and talk to you a little bit about what it's like working as a chemistry scientist. I work here at QUT. I'm a lecturer. That means I teach university students very similar to yourselves. But also what I do is research, specifically in chemical science, and more specifically on a field of science called polymers. I'm here today to tell you a little bit about the amazing world of polymers. Let's head to the lab. Hi everyone, welcome to the lab. Let's try some experiments. Here I'm holding a little vial of phosphorus, just the element phosphorus all by itself. In this form you can see the nice colour. The colour is red, so we call this red phosphorus. And we'll talk about the fact that phosphorus can exist in a few different types of colours and a few different types of chemistries. Now, as you can see, this red phosphorus is relatively safe and stable. I'm here holding it in my hand in this vial. But let's see if we can use some chemistry to make it just a little bit more reactive. How about that? My phosphorus has become just a little bit more reactive, you would say. What does it look like to you? I think it looks like a big burning sun, so I call this my red phosphorus sun. So what's going on here? Here we've got red phosphorus. Now that you've seen how reactive it can become, you might have noticed that you've seen this before. So the red phosphorus is relatively safe and stable. But if we apply any heat to red phosphorus, we can convert it into another form called white phosphorus. White phosphorus is very, very reactive and instantly starts to burn when exposed to oxygen, which is what I've got in this flask here. Can you think about something where you have seen red that you apply a little bit of pressure and heat to cause it to ignite? Matchsticks are usually red, aren't they? Red phosphorus is what most matchstick heads are made out of. When you press it against the side of the box and you flip it, you're applying a little bit of heat and pressure, and that converts some of the red phosphorus into white. Once it starts to burn, it continues to convert all the other red phosphorus into white phosphorus and lights your match on fire. Now, this is a really good demonstration of how we can use the power of chemistry to convert one chemical or molecule into another to create energy or work or some kind of function for us. Today, I'm going to talk to you about polymers and how we can use the power of chemistry to change the properties of polymers and create many of the different materials that we see around us today. So what are polymers? We've probably started to learn a little bit about organic molecules and compounds. Polymers are a specific type of organic molecule, typically organic molecules. So molecules we know are different atoms bonded together to form a unique compound. In the case of polymers, what we have is lots and lots of molecules bonding together to make extremely long chains of atoms and extremely long chains of molecules. Now this is quite interesting because the molecules have such a long chain-like structure, they have very interesting and unique properties. The most likely place that you've seen polymers are all the plastics around you. The chairs that you're sitting on, the water bottle you might be drinking out of, the TVs, your phones, there's plastics all around us. They are incredibly amazing materials. And it is that long chain structure of polymers that give them such amazing properties. Now, to prove to you that polymers are made of long chains of molecules, let's do an experiment. Here, I've got a flask that you can see, and you can see it's got two layers of two different liquids. On the bottom, we have an aqueous layer or a water layer, and I've dyed that purple just with a little bit of a dye. On top of that, we have an organic layer or a hydrophobic layer of a different type of molecule. Now we can see that these are two liquids, right? There's two solutions on top of each other. Now if we have two solutions that won't mix, we call that immiscible. But let's see what happens when I reach in with my tweezers. What do you reckon? Does that look like a long chain molecule to you? Do we still have a liquid or do we have something else now? It's flexible, but it's actually a solid. So what's going on here? We're doing a chemical reaction between two liquids to make a solid material. And that solid looks like a long chain. So if it looks like a long chain, it's a good hint that we might have a polymer here in front of us. Now, does this polymer look maybe familiar to you? Have you seen anywhere where you have a long, continuous chain or fiber that you might use for, say, clothing or sport? I like to go fishing on the weekends, and this looks a lot to me like fishing line. And that's because what I'm making here is the exact same material that fishing line is made of, which is called nylon. It's one of the most popular polymers in the world. Now, if we know we can make fishing line out of it, it's very, very strong. It's also very flexible, right? It can go into the water, it can go around snags, trying to catch fish. But when our big, big fish comes along and takes the hook, then we know that it's nice and strong and doesn't break. Now, nylon's not only used for fishing line, it's used in a lot of different places. Maybe you've worn a pair of stockings before, or somebody you know has. Stockings are also traditionally made of nylon. Now they're nice and soft and flexible as well, but they're not as strong as fishing line, right? But I don't know about you, I don't think I'd want to wear stockings made of fishing line. It's not very soft and smooth. So the nylon that they make for stockings is made to be extremely soft and smooth and feel really nice against your skin. So that's cases where we see nylon as a long, flexible fiber, we call these. These are plastic fibers. So this is one of the really, really unique things about polymers, is that we can very, very easily change the properties to make it stronger, more flexible, softer, whatever properties we need, we can dial that in when we make polymers, and we can perfectly make it for the application that we need. Now, what's happening here when I'm making my nylon is I have two solutions of two different molecules. Now, we said polymers are made up of long chains, and each of the individual rings in our chain, or our links, are called a monomer, or a single molecule. Now, in this nylon demonstration, what we have is two different monomers, monomer A and monomer B. In the purple solution on the bottom, we have monomer A, and it has two reactive groups on it. But those reactive groups won't react with itself. So monomer A is happy by itself in solution. Monomer B is in our organic layer on top. And again, it has two reactive positions. But again, neither will react with itself. So both monomer A and monomer B are in their individual solutions happy. Just where those two layers are touching at the interface there, monomer A can come into contact with monomer B, and they are set up to do chemical reactions. So what happens is monomer A reacts with monomer B and makes a covalent bond. Now both monomer A and monomer B still have an unreactive site. So monomer A can react with another monomer B, and then monomer B can react with another monomer A, B, A, B, A, B, all the way along until we grow our chain out, and we can pull out a nice polymer fiber. And so that's what I'm doing. When I reach in, I'm just grabbing the layer of polymer that forms at that interface, and then as I slowly pull it out, more and more polymerizes is the word we use. We make more polymer, and we can continue to draw this fiber out. Now this is very similar to the way that it's made on an industrial scale. Of course, it's not a single person pulling it out like this. They're using large instruments, large machinery, but the process is the same, of mixing these two solutions at an interface and then drawing out a nice continuous fiber. So hopefully that's given you a bit of an idea of what a polymer looks like. But we should start talking a little bit about some of the different applications of polymers and plastics.
Start talking about the applications of polymers. Let's start with something that is probably familiar to you. Do you recognize these symbols up here? What do they mean? Go on, shout the answer out at the video. Unfortunately, if you said that these symbols mean that the plastics are recyclable, that's not exactly true. These symbols indicate to plastic recyclers what the classification of each of these polymers are. So this triangular symbol with the 3 arrows doesn't mean that it's recyclable. It's saying to the recycler, this is plastic number 1 through to 7. The reason why it doesn't mean that they're recyclable is because even this number 7 class here, they're all polymers that can't be recycled, all fall into that category. So that category itself is not actually recyclable. So only the first 6 of these polymers can actually be recycled. And unfortunately in Australia, typically only 1, 2, and 5 are actually recycled. So we've got a long way to go. But let's have a look at what these different symbols mean. So they're referring to different classifications or types of plastics, and in particular, the types of polymers that they're made out of. So here in the second row are the names of the different types of polymers. And we'll have a look at a few of those. So let's look at number 1. Number 1 is polyethylene terephthalate. So this is a nice recyclable polymer. This is the one that you can now get 10 cents for taking down to your containers for change for recycling. And this is typically things like your water bottles, your soft drink bottles, your Powerade bottles, kombucha, all of those types of plastic bottles. And you can see here, I've got in my picture a nice collection of these different types of bottles. Now, as you can see, they can come in all sorts of different shapes. And that's one of the advantages of plastics, is it's very easy to form different shapes, different sizes, and to make even interesting patterns. Now, some other advantages of this polyethylene terephthalate is that it's somewhat flexible, so you can squeeze the bottle to get the last little bit of drink out. You can collapse it for recycling, which is useful. You can, if they're not water soluble, which is good. So the drinks don't actually dissolve the bottle, which is, really an important part of what's going on here. The other thing is that the plastic itself, if you have a look at the bottles over here on the left, is really nice and crystal clear. And this is why it's commonly used in commercial drink products, where you might want to be able to see how great the drink looks on the inside. Alternatively, it's very easy to color it into very desirable colors. So PET is very popular for its marketability. Let's have a look at another drink bottle plastic that you're very familiar with, which is probably this one here, a milk bottle. So these are made from high-density polyethylene, and you can see that they have the same function as PET. So they can be shaped into interesting shapes, such as the cube. These cube shapes are really good because they're very efficient packing. There's not very much airspace when you pack multiple bottles together in a box. They're waterproof as well. They don't dissolve with the milk on the inside, and we can easily carry them with a nice handle. So, again, the plastic's very useful here. But what's the big difference that you notice between the high-density polyethylene and the PET? So you might notice that the plastic here for milk bottles is typically not clear. If it's this high-density polyethylene, it doesn't ever appear clear. And that's one of the downsides of high-density polyethylene. So if you have a really pretty drink, you might not want to put it in high-density polyethylene. Milk, I think everybody in the world knows what milk looks like. It pretty much always looks the same, and you can't really commercialize the look of milk. One of the advantages, though, of this opaque coloration is that less light gets through the bottle, and less light on your milk means that your milk will last longer because there'll be less spoilage of your milk. So you can see that actually we can use that as an advantage. Now, high-density polyethylene and PET are both examples of recyclable polymers. So why is it that some polymers are recyclable and some polymers aren't? So to understand whether a polymer is recyclable or not recyclable, we need to think about its molecular structure. So we saw earlier in our nylon demo that polymers are long chains of molecules. So if we were to sort of take some kind of microscope and zoom in on what we're looking at, here you can see the long chains of molecules present in a plastic. So broadly, we can class polymers into a couple of different classes. The first two we'll talk about are thermoplastics and thermosets. Now, thermoplastics are inherently recyclable. And why is this so? So we've seen these long polymer chains. We did the nylon demonstration, and these long polymer chains are connected with strong covalent bonds between the molecules forming our polymer chain. And we talked about that already. Now, when we put multiple polymer chains together, there's actually weak chemical bonds in between the different polymer chains. So these are our intermolecular forces, things like hydrogen bonding, van der Waals forces, ionic bonding, these types of interactions that aren't as strong as covalent bonds, but they do help to hold the polymer chains together. And that's really good because that gives the plastic structure. So the way I like to think about this is when you boil a pot of spaghetti or a pot of noodles, all the noodle chains of the spaghetti or the noodles, the mee goreng ramen, actually twist together in the pot, right? Now, when we try and grab just a few of the noodles or few of the spaghetti out, what happens? The interlocked chains actually pull on each other, and it's very hard to just pull out, say, one noodle. You always tend to bring a couple. So this is something we call in polymer chemistry or polymer science, chain entanglement. And it's that entanglement of those chains that help to give the polymer structure, give the plastic structure. Also, you can think about the little stickiness between the polymer chains. That's almost like your weak intermolecular forces. It helps to hold the chains together, but you can actually still pull them apart without breaking the spaghetti. So now when we think about our plastics, if we apply energy to our plastics in the form of heat, then we can actually overcome these weak intermolecular forces in between each of these chains. And then we can actually start to stretch them out and align the fibers. Now, this is really interesting because this allows us to melt our plastic. And this is why all our thermoplastics are recyclable. Because if we heat them up, the chains can actually start to move past each other We can melt them back to a liquid, and then we can reset them and make them into a new product. We can melt down plastic bottles and make new plastic bottles. Let's compare this now, though, to this other class of polymers, which are called thermosets. And these are a really interesting class. Here, the difference is that in between the different polymer chains, where these little circles are, we actually put strong covalent bonds. Now, this is actually linking the polymer chains together with the same sort of chemical strength as the bonds in the back of the polymer chains, in the backbone. Now, the way I think of this as an analogy is you've made your pot of spaghetti, and for some reason you go and get a tube of superglue, and you squirt superglue all the way through the spaghetti and let it set. They're like your crosslinks. Now, think about how that bowl of spaghetti will work. Are you able to pull a few chains out past each other anymore? No, they're going to be stuck together, right? The other interesting thing is if you turn the pot out and the spaghetti comes out, what shape does it hold? It'll hold the shape permanently of the pot, of the mold that you've used. Now, where this is interesting is that when you take thermosets, because you've got these really strong chemical bonds, when you heat these up, they no longer have the ability to slide past each other. We can't melt these plastics anymore because these strong chemical bonds won't break without breaking the whole polymer structure. So let's think a little bit about the difference between these two in terms of some materials you've probably seen. So you've probably got one of these in your school bag, a lunchbox. These are made from polypropylene. Now, polypropylene is plastic number 5 and it's recyclable. So it's a thermoplastic. So if we think about our polypropylene, if we put this in the microwave and we heat up our lunch, does the plastic melt? Of course it doesn't, otherwise what would the purpose be? So there's some ability for these thermoplastics to resist melting. You know, those weak intermolecular forces between the polymer chains can be changed and modified to increase the strength of the plastic. Now think about what happens if you were to say, decide you wanted to heat your lunch up faster, so you put it in the hot oven to try and heat up your lunch. What's going to happen? Firstly, I think your mum is going to yell at you for having done that, because of course the plastic isn't going to melt. So the plastic will start to melt now, right? It'll melt down through all the oven racks. So you can see that there's like a threshold. So it can handle the heat of a microwave, but an oven is way too hot. So that's how we can tune the properties. We can change just the strength of those intermolecular forces between our polymer chains to make them much, much stronger. Now, if we think about our oven, we can think about some plastics we actually regularly put in the oven. So these silicone cookware are becoming increasingly popular. You've probably seen them at your kitchen shop. Cookie molds, cupcake tins, baking pans. So we can put this plastic silicone into the oven and it won't melt. And that's because silicone is a thermoset. So it's much more heat resistant. And this is advantageous because we can now use this for cookware, and then we get all the extra plastic properties that help us with our cooking. So the plastic silicone cookware is good because it's flexible, so you can still pop out your cooking rather than a metal tray. So it can make it easier to get your cookies out or get your bread out. The other thing that's nice is it's very easy to make lots of different shapes with plastic. So you can have very interesting shapes and sizes and everything like that compared to, say, metal. Now, again, this heat resistance doesn't last forever. The silicone cookware can survive your oven, but if you decide to go camping, I wouldn't suggest you try and use this cookware on your campfire, because there it'll actually start to burn. And you'll probably notice that it won't melt. It'll actually just start going black and giving off smoke and charring. That's because it won't melt because of the thermoset structure, but it does burn because it's made of organic materials. So that's a bit of an example of thermoplastics and thermosets and comparing how the molecular structure of those two affects their properties. Now, these aren't the only classes of plastics. There are others. And one I want to talk about are these guys here. Does anyone recognize what I've got in my hand? Not really a trick question. It's a nice rubber band. Now, have you ever thought about how amazing rubber bands are? Think about it. I've got this rubber band. It's got this size and shape. And I can pull and change that size and shape quite a bit on my rubber band. And what happens when I let go? It snaps back to pretty much exactly the same size and shape that I started with. And I can do this hundreds, if not thousands of times. Now, what's going on here? Rubber bands fall into a third class of plastics called elastomers, and they're actually somewhere between a thermoplastic and a thermoset. So the elastomers have lots and lots of this thermoplastic type structure where you've got polymer chains interacting via these weak intermolecular forces tangled together. But you also have just a few of these stronger thermoset chemical crosslinks. So when I pull on the rubber band, I'm putting energy into the system and I'm overcoming the weak intermolecular forces and I'm pulling the thermoplastic chains past each other, stretching them out. Eventually you get to a point where you can't pull a rubber band anymore without breaking it. And that's when you hit the thermoset structure, the strong chemical crosslinks. So as long as I stop before that and let go, the thermoset part of the molecule actually remembers what the sort of structure is like. We call this shape memory. So it actually pulls back into the structure and resets all of the thermoplastic type interactions. And so this is something, like I said, we call shape memory. And this is really interesting. We're researching this a lot in chemistry research and polymer research because we want to make materials that can actually move and make motion potentially without any kind of motors or robotics. So this is the field of soft robotics. And there's very interesting things people are doing with sort of soft plastic jellyfish that can move through the water without any motors, just using the power of shape memory. So far, we've focused a lot on polymers that we see every day, and all of these polymers I've shown you so far share something in common. They are what we call synthetic polymers. That means they're made from crude oil as their source of materials of building blocks. Now, this can be problematic because there is only a limited amount of crude oil, and that's not going to be renewable. So we need to think about other places that we can source plastics and polymers from. And one really great place to do that is nature. When we take a plastic from nature or a polymer from nature, we call this a biopolymer, biological polymer. So let's have a look at one of those.
So let's talk about the biopolymer alginate. Where do you think alginate might come from? Did you say algae or seaweed? Why do you think that? If you said it's because it's green, it's a little bit of a trick. I've put some green food dye in here just to make it look more colorful. Normally this is a really yucky yellow color. But it is a biopolymer from algae or seaweed. In particular, seaweed makes lots of this. And it's the structural component of seaweed. We talked a little bit earlier about cellulose and how that's the structural component of land-based plants. And we use that to make things like cotton and paper. Well, alginate's an interesting polymer in seaweed and has very different properties to cellulose, but it plays a similar role. It's the main structural polymer for the formation of seaweed. But let's try an experiment. You can see here that my alginate is a liquid and I'm drawing it up into my pipette. And I have two beakers here with solutions of sodium chloride and calcium chloride. Now, I want you to remember particularly the positive ions, the sodium ions and the calcium ion, because that's what's going to do our chemical reaction here now. So look what happens when I drop my alginate solution into my solution of sodium ions. What can you see happening? Is the solution going green? The alginate's just dissolving in the sodium ions and making a nice green solution, right? So we can say that the alginate can dissolve in the solution of sodium chloride. But let's compare that to what happens with calcium chloride. What do you notice happening? Is it still dissolving? What can you see in the beaker? Do you see little solid balls? So our alginate is not dissolving in our calcium chloride solution in the same way it did with our sodium chloride. Watch what happens when I go a little bit faster. So what's happening? What do we think's going on? Whenever we do science, we should ask ourselves questions about what's different between our two experiments. What's the difference between our sodium chloride solution and our calcium chloride solution? And of course, the only difference is our sodium ions and our calcium ions. Now, we need to think a little bit about the structure of alginate. So alginate is a biopolymer, and it is made up of long chains of polymers that have negative charges all the way along its backbone. Now, those negative charges on the backbone of the alginate are going to interact with the positive ions in our solution, either our sodium or our calcium. Now, our sodium ion has one positive charge. So if you have one positive charge on a sodium ion and a negative charge on an alginate molecule, how many chemical bonds can they form? That's right, they can form one ionic bond per ion pair. So one sodium ion bonds to one charge on the alginate, and what we end up with is sodium ions all along the backbone of our alginate. But that just means we have a nice charged balanced polymer in solution, and it dissolves up easily. Let's think about our calcium ions though. Calcium is one more group over in the periodic table. It's in the second group, and so its charge is 2+. How many ionic bonds can calcium form with the negative charges on alginate? That's right, 2. 2 positive charges can interact with 2 individual negative charges on the alginate. Now the difference is that the calcium can form 2 bonds between 2 chains of alginate, and these form little links between our polymer chains. These are the cross-links that we saw, similar to our thermoset polymers that we talked about earlier. And so when they form these crosslinks, we are now making a solid material, and that solid material doesn't dissolve in the water. Now the polymer is still quite flexible and quite soft, and it's actually edible. I'm not going to eat this because I've made this in the lab, but if you make this in a food facility, you can eat this kind of material. And you may have consumed something similar. This alginate appears in medications like Gaviscon for heartburn, because it helps to set a layer in your stomach to stop the acid reflux. The alginate and similar biopolymers are used a lot in foods as thickening agents, as gelling agents. You might have had starch-based polymers from tapioca flour in your bubble tea. Or another related polymer, of course, that you probably are all familiar with is gelatin in jelly. So we've just finished talking about alginate and gelatin, and we've talked about how these are biopolymers because they come from natural sources. While they are biopolymers, they also form a different class of materials that we call hydrogels. These are polymer networks where we have lots and lots of water trapped within the polymer chains. Think about when you make some jelly at home to eat for dessert. You pull out a sachet with a small amount of powder in it, and you pour hot water onto that powder. You then put that in the fridge and let it set. So very little bit of that powder forms all of that big bowl of jelly that you're going to eat. Let's have a look at another type of hydrogel. This one is quite an amazing one. This is sodium polyacrylate. This is a synthetic polymer, not a biopolymer, but it is also an extremely good hydrogel. So you can see here I have a nice fluffy white powder of sodium polyacrylate. I've put 0.5 gram of sodium polyacrylate in this beaker here, and let's see what happens when we add some water. That's pretty amazing stuff. Very quickly, we can see that the sodium polyacrylate has soaked up all of that water and has formed a gel-like material. So I said that I put 0.5 gram of sodium polyacrylate in here, and I've added about 50 milliliters or 50 grams of water. That means that in this beaker, only 1% of the material in there is actually polymer, and 99% of that is water. And that's typically the definition of a hydrogel, is that very small amounts of solid make up the network, and it's mostly water. Now this is quite amazing, and again, it's something that you've definitely seen before. Where can you think about might be a good place to put a powder like this to soak up large amounts of liquid? Okay? It's useful because it doesn't spill everywhere. The most common place to find this material is in nappies. That's exactly actually where I have gotten the sodium polyacrylate from. I've cut open some nappies and shaken the powder out. And you can see why that would be useful, right? The nappies are really, really good at soaking up all the urine from your little baby brother or sister and stop it from going on the floor where you step in it. And so you can see that this small amount of powder is able to soak up large amounts of liquid. And aren't we grateful for that? There are definitely some other places that you'll know or recognize this material. Maybe you're familiar with the toy called Orbeez. Small little plastic beads, you place them in water and they soak up and become much, much larger and they swell. I know Mr. Beast tried to fill his entire backyard with Orbeez, right? So those Orbeez are made from the exact same material. The only difference is that they're pressed and made into a little ball shape. Your mother might have had some similar things that she put in like a vase or a pot plant, and they soak up water and make up some nice decorative balls as well. There's also another very interesting place where this gets used. In Australia, we grow lots of animals for food, such as sheep and cows, and we often send those overseas to other countries. Now, if we think about putting animals into a pen on a ship, and then we put a water trough in there, and we fill the water trough with water so the animals can drink. Now imagine what happens when that boat goes over the ocean. What happens to the water in that trough? It's simply going to splash out and spill everywhere. So often what they do is they use this kind of material to soak up large amounts of water. They can then put this into the water trough, and the animals can safely eat this material. It's not dangerous. And the nice thing is that it's 99% water and only 1% polymer. So when they eat it, they're actually getting lots and lots of water. So this is a really nice way to deal with water on ships. Now this is not the only example of where we have polymers interacting with a different molecule. In this case, it's water. Let's look at some other materials that integrate different molecules in their network. So we've just finished talking about hydrogels. Let's look at what happens when we use polymers to trap other states of matter. Here in this plastic cup, I've got the components of a polymer called polyurethane. Again, this is a system where we've got two different components we need to mix together. But when we pour this solution into here, we'll do a chemical reaction and make our polyurethane. And we'll see what else happens as well. Wow, that's pretty amazing stuff. What does that look like to you? Maybe it looks like some crazy science experiment you've seen before. Or maybe it looks like something a little bit more familiar that you might do regularly at home. Is anyone a MasterChef fan? Can anyone think about something that they often cook on MasterChef that looks like that raises up out of the container? I think it looks like a souffle to me, the way that it comes up out of the cup. And we can actually think about the fact that what we do when we bake desserts is very similar to what we're doing here. So what do we think about when we bake? What are the main ingredients? There are 3 key ingredients to all dessert baking: flour, baking soda, and egg. You also have things like sugar, butter, chocolate, strawberries, but they're all just added for flavor. The 3 structural components are that flour, egg, and baking soda. So what's happening? Where does flour come from? It comes from wheat, right? Flour is actually our source of our polymer when we bake. Flour is actually made from starch, which is a different type of polymer that comes from plants. Earlier we talked about cellulose. That's the main structural polymer in plants. Starch is what they use to store energy, and they use it in their roots and in their seeds. And that's where we get the flour from the seeds of the wheat plant. So that is our polymer that we're going to form our network out of. The next ingredient is our eggs. Now the eggs form chemical bonds between our polymers, our starch polymers from our flour. So then we go from our liquid, like we saw with alginate, to our nice solid structure. So instead of using ions or sodium ions or calcium ions, here we're using the proteins out of eggs to form those chemical bonds. So that's what forms our polymer network. But why do we get the nice fluffy texture? The key ingredient is the baking soda. Baking soda produces carbon dioxide as you cook in a chemical reaction. Think about if you've ever made a baking soda volcano. When you mix the vinegar with the baking soda, you form lots and lots of carbon dioxide very quickly and it foams up. When you bake, you do the same process, just a little bit more slowly. The baking soda produces carbon dioxide that gets trapped within the starch polymer network of the baking, and that's what allows it to rise, and you end up with little air pockets all the way through your nice cake. We have almost the exact same process going on here. Here we've got our polyol component of our polymer, which is one molecule. You can think of it as our flour or our starch. I then mix in the second solution, which contains 2 things. One is called isocyanate. That forms chemical bonds between our polyol and forms our nice solid network. The other chemicals in there produce a gas, and as it produces a gas, it starts to foam up our network. So what we end up with is a nice polyurethane polymer with little air pockets all the way through it. And so we have a nice spongy molecule, or nice spongy material. And this is just a foam. This is a sponge foam. I buy this kit from a craft store, so you can do this yourself. Now what's interesting that you can't tell through the internet is actually this cup is nice and warm. So when we do our chemical reaction, we're giving off heat. Now when we do a chemical reaction that gives off heat, what can we say about it? How can we describe that chemical reaction? We would call it exothermic. It gives off heat to the universe. Now we took the 2 reagents in the 2 different containers and mixed them together, and the reaction happened almost instantly. So if a reaction happens almost instantly, it gives off heat, it's exothermic, we can also describe that reaction as spontaneous. So there's a little bit of chemical thermodynamics right before your eyes.
So far in today's lecture, we have focused a lot on plastics. These are materials where the bulk of the actual composition of the material itself are polymer chains, and not a lot else. Maybe a few little dyes or stabilizers, but that's it. But we've seen some examples in the last couple of experiments where we have materials, where we have the polymer in some other kind of molecule. We have very interesting properties. So we just saw the example with the polyurethane foams. So here we have our polymer matrix in yellow, so that's our polyurethane. And then we have our gas bubbles in between, making what we call pores in our polymer network. In this case, it's probably carbon dioxide foaming up from the reaction mixture when we first make that polyurethane foam. We saw sodium polyacrylate. That was an example of a hydrogel. So here our yellow matrix is our sodium polyacrylate polymer, and that was our dry powder. And then as soon as we added water, the water was drawn up into the pores of the sodium polyacrylate and caused it to swell up into the nice hydrogel. The last class of these types of materials I want to talk about are composites. And that's where instead of having a liquid or a gas, we have a solid within the polymer matrix. So this might be something like clays, silicas, glass. You might have heard of glass fibers for fiberglass. So that's, particles of glass held within the polymer matrix. Or more recently, you've probably heard a lot about carbon fiber. And that's where we have carbon-based materials in between our polymer matrix. Now, what's interesting is when we think about how these materials behave when we start to apply some stress, and you've seen some of this in the video. So if we think about having a block of each of these materials and we were to press onto those materials from the top, look at the different types of ways they react. So in our polymer foam, we know that we can squish that down really, really far because the air can come out of the pores. In our hydrogel, you saw that when I squeezed it, that the water would come out, but also interestingly, it would actually start to fall apart and break apart. So think about if you've ever played with Orbeez. When you squeeze Orbeez, they tend to break up, don't they? Orbeez are a hydrogel. With our polymer composites, what's interesting is that the really, really hard non-plastic material within the matrix really helps to resist the pressure. And that's where polymer composites are really, really useful. They're good in really high stress applications where you need to resist a lot of force. So that's why you often hear about polymer composites being used in bicycles or race cars or even in rocket ships. And then we can think about what happens when we remove the force from our materials. So we saw with our polyurethane foam, as soon as I stopped touching it, it would spring back. And we know this for any foam or sponge. They're nice, the pores will come back and they refill with air. With our hydrogel, because the polymer matrix is typically very weak, it doesn't tend to spring back. It doesn't seem to tend to draw back the water. And usually we end up with that structure damage being permanent. Here just behind me, if I move out of the way, you can see our composite. It basically maintains its size and shape. So maybe it comes back to the original shape, maybe it holds on to the new depressed shape, but either way, it's very similar to how it started at the beginning. And again, that's really useful. If you're riding a carbon fiber bicycle or a carbon fiber aeroplane, you really want it changing shape every time it got experiencing forces. So these are some of the advanced applications we have for polymers. Now, polymers can actually be a lot more than just materials and plastics. And they can also have very different structures. So I've shown you a lot of polymers looking like this up here with long chains of monomers. And there's lots of different ways that we can make those. We can change the way that the different monomers form the structure. So we have sort of random mixtures of monomers A and B, for example. We might actually organize them. So we can say that we want all monomer A first and then all monomer B. And this can give them very interesting properties. Now, polymers don't have to be long chains. They can come in all sorts of sizes and shapes. I've done a lot of research in my career on these hyperbranch polymers. Instead of having long polymer chains, we have this branch type structure. And this is really interesting because these branched structures are more like balls and less like chains. And now when you think about filling up a bucket with balls, they don't entangle in the same way that our chains do. They don't act like spaghetti. And so this means they have completely different properties to our linear polymers. We can also have things like cone polymers, where we have one really long polymer chain as a backbone, and then lots of little short polymer chains going all the way along. And these are very interesting because they mimic a lot of the polymer structures we see in nature. There's lots of different other types, but probably my favorite class are this group here. Here on this picture, they're labeled dendritic linear, but another name for this class of polymers are called arboreal polymers. And arboreal means tree-like. What do you think? Does that structure look a little bit tree-like? So I hope you've enjoyed today's virtual lecture. It's been a great pleasure putting this together. I hope I've given you a little bit of an idea of what a polymer is, the chemical structure, how our known understanding of chemical bonding helps us to understand how polymers and plastics behave, and how we can change those for lots of different applications. I'm going to join you very shortly via video call, and so hopefully I get a chance to answer your questions. Thank you very much.